Hello, everyone. Welcome to the online seminar on the mathematical foundations of data science. Thank you all for joining today. Our seminar is generously sponsored by 2 Sigma. It's my great honor to introduce our prestigious speaker, Professor Yao Xie. Professor Xie is an associate professor and Harold R. and Mary Annie Nash early career professor at Georgia Institute of Technology in the Milton Stewart School of Industrial Engineering, Industrial and Systems Engineering. She is also an associate director of the Machine Learning Center. She has made great contributions to research areas including statistics, in particular sequential analysis and sequential change point detection, machine learning, and signal processing. Her works provide the theoretical foundation and developing computationally efficient and statistically powerful algorithms. She has also worked on problems in sensor networks, social networks, power systems, crime data analysis, and wireless communications. She received the NSF Career Award in 2017. She is currently an associate editor for IEEE Transactions on signal processing, sequential analysis, design methods, and applications, and the Informs Journal on Data Science. She also serves on the editorial board of Journal of Machine Learning Research and is an area chair of NeurIPS. The title of her talk today is Statistical Inference on Spatial Temporal Networks, Two Tails, and More. Without further ado, please join me in welcoming her.
Okay, great. Thank you so much, Dr. Yang, for the very generous and kind introduction. And thanks a lot for inviting me to this very prestigious seminar series. Since the word has been used, I don't think I'm prestigious, but the seminar series is definitely a very one of the top seminar series I enjoy as an audience myself as well. All right, so I guess today the seminar lasts for about an hour, and the talk hopefully will be about 50 minutes with questions. Okay, so with that, I'll start. And so basically today I'd like to talk about my recent research on the topic of spatial temporal networks. So you're wondering what this is. So it's basically a type of point process model that we aim to capture discrete events data happens over spatial temporal setting and over networks as well. I will talk about two tails and some expansions around that. All right, so let's get started. So what is purpose here? So we are interested in estimating networks in high dimensional streaming data. So for example, one setup is to consider continuous time setting, the continuous time network estimation. So the the observation happens over continuous time. The second setting is discrete time network influence estimation. So I'll talk about these two aspects in this talk. So what is spatial temporal networks? In particular, for example, we're interested in social networks where the network is clearly dynamic. Every day when we use social networks such as Facebook, LinkedIn, Twitter, information are being generated by users. And we can observe, for example, how users interact with each other, how the information is propagating over networks. This is one of the important questions in social network. How do we understand how information propagate dynamically over networks? Can we infer people's interaction, their connection, and community structures? And the second example is in this is actually neural networks. So that's how human brain function. So scientists can collect data using different methods, for example, EEG or ECG, and in situ study will generate sequential data. We can observe so-called neural spectrum data. And one important question is understanding how neurons activate each other. So study the activation pattern that has been modeled using so-called Hox processes, as I will explain later as well. So that's a related question here as well. How to understand brain maps and neural functions using discrete events data, which are these neural spectrum data. And another one is seismic activities. So in this setup, geophysicists collected a large size so-called seismic catalog, which records the time, location, and the magnitude of the earthquake happens over the entire globe. And so these seismic activities can trigger with each other. So one thing happens here, and there will be the subsequent events, aftershocks, and there's also foreshock. So being able to understand these seismic activities across space and time will be able to help them making predictions, understanding what is happening there. And so seemingly unrelated, but actually crime activities is also a type of spatial temporal data. The data is generated by, of course, these criminals. So the data is kept record by the police officers. Whenever you call 911, that triggers an event. The police officer will arrive at the scene, start investigation, and keep record in the police report saying where and when there has been an event. And there is a pretty well-known hypothesis in criminal data analysis that the crime events triggers each other. Once some type of crime events happens, for example, burglary, and this map actually shows part of Atlanta, and there has been 23 serial burglar breaking into the houses. And later on, it's find out all of these are done by the same person. So clearly this person is very good over the past 6 months. So be able to understand how these events relate to each other can help them, understand how the crime hotspots is formed and hopefully catch the bad guys before 23 cases has been done. And of course, these days, this is probably on everybody's mind, COVID. So COVID transmission over space and time, the dynamic, for example, every day we can observe how many cases there are in each location. And that is a type of spatial temporal data as well over space and time. So lastly, power grid, for example, when there is a, some outage happens at one place, and this can cause the so-called cascading failures that propagate over the networks. And so the small scale power failures can propagate becomes a major one. So how do we understand these cascading patterns over the power grids is also the target here. So far, we have seen two kinds of problems. One is something happens over space. The other is happens over networks. Naturally, there's a network structure. So I would like to point out actually in this talk, in our work, we're gonna treat the spatial correlation mostly by discretization. So once we discretize it, each discrete location can be related to other discrete location. So in this setting, we're gonna consider them in the same setup. And as we have mentioned, lots of so-called discrete events data are generated on these in these problems that provide information about these networks. And these data are in a format of discrete events in time, location, and the marks. So when this happens, where this happens, and the additional information which are called the marks. For example, social network tweets is about when and which user. So location here denotes the nodal index in the Twitter setting. And the marks are going to be these tokens, right? So these short messages can't be too long. And so we can represent it by tokens that provide additional marks to them. And neurospectring is for each neuron, where that's going to be the neuron, and the marks could be, for example, the magnitudes. And earthquake catalog is when and where and how large is the magnitude of the earthquake. Police report records the time, location of the crime events, and also some structured information about the type of crime and so on, and also unstructured information, which are these detailed documentation of the police incidents. That's in the form of a paragraph. Sometimes can be long, but entered by the police officer. That's going to be the marks here. So it has a natural language processing component to this as well. And like I mentioned, COVID data is daily cases happens in thousands of counties in the US every day. And using this, we can understand how COVID spread and possibly figure out the effective intervention scheme and power outage data. Okay, so I think there are probably, this kind of data can be familiar with the audience, but may not. So I'm going to give some basic information background for what is point process data, why is it different from traditional data. And so these discrete events data can happen at any time, and there's complex interdependence between different dimensions. Here, each dimension can be one node in the network or one location in the spatial temporal setting, and there can be different kinds. So there are marks. So these different shapes represent the marks. The arrows represent the dependence between the events, and so it's asynchronous. So this is different from traditional IID setting assumed by statistical model, where you can see, essentially it's assumed in a discrete time setting where the samples has been taken, and so they're aligned in time. You're talking about indices as a discrete index x1, x2, x3, and so they're independent. Then you only have dependence across dimensions, but not across time. In time series data, there can be dependence across time, but across dimensions, but still it's going to be this discrete index. That means assuming the sample has been binned or has been aligned. So this is going to be different. And we're interested in considering continuous time because timing of the data points also carry a lot of information. For example, in crime events, for two events that happens very close to each other of similar nature, that tells something. It could be done by the same person. So if they happen further apart, like if they happen just over 2 days versus it happens over 2 weeks, this time duration is carrying a lot of information. So we want to capture that in the model as well. And in particular, it is important to consider so-called triggering effects or influence between events. So for example, this is one example. If in seismic data study, when there is an earthquake happens here, and as time goes on, another earthquake happens, but how do we know the other one is actually triggered by the previous one? So can we find this, and how does this trigger, how long it takes for another earthquake to happen, in which direction, and how this influences propagate over space and time is a fundamental question we want to infer here from data. And by the way, so we have some project with Dr. Zhigang Peng at the School of Earth Science studying the earthquake triggering effects. And so this influence also happens in crime data. Like I mentioned, in criminology, there is a famous theory called the broken window effect. Once neighborhood has a crime incident, similar crime is more likely to happen. So I give this example of Atlanta. This is Buckhead area, which is a affluent area in Atlanta, actually. So during 6 months period, the same person, the staff is clearly very good, break into 22 cases of houses. And so actually, I think my house is somewhere in the middle here. So I would say, when I look at this, I feel for the first time, my research is directly relevant to my life. And so I'm surrounded by this serial offender. So we want to be able to study the triggering effect. And if we can do that, hopefully catch this bad guy before it is too late. And so the COVID, this is an example of COVID-19 data. And you can see over past year, we illustrate the number of confirmed cases over thousands of counties in the United States. And so in this example, each dimension is one county. So the spatial location is naturally discretized. And so by understanding the influence, we can say if there is one hotspot at one location, how this will transform and influence the future cases in the future. And so the network formulation will be able to capture things such as you consider nearby counties. If there's a hotspot in one location, then nearby counties will become hotspot very likely in the future. And this can also capture the fact that major cities will, an airport, for example, major air hubs, transportation hubs, will have longer range influence, like things happens here, can influence other major air hubs in the United States. So this influence doesn't happen, decay smoothly over space, but have this long-range dependence over a network. So just to mention, we have 2 works on this topic. If you're interested, you can find out on my website. All right, so with all these examples and application from real world, in summary, we want to be able to recover underlying network that captures dynamic. One thing happened at one location, one node, how this will trigger future events at other nodes. And so estimating this influence. Using this kind of discrete events data, which can happen asynchronously over time. So application summarized here. Why this is important? Clearly, once we have this, we can understand the network structure. We know how the events are being, the influence is going to be propagated. And so this can help us to make prediction for the future events. And this can also help us to monitor, for example, detecting hotspots in COVID-19. If we understand how this propagates, what is the most likely location to be a future hotspot, and we can hopefully detect this quickly. And also causal inference that can be inferred from the underlying network structure. For example, in neuronal network study, we want to understand which brain region has a causal relationship with another part of the brain region. And finally, based on this model, we could also make statistical decisions, optimizations, such as intervention. What is optimal intervention scheme? All right, so hopefully that gives a picture what we're trying to achieve here. And this is the outline for the rest. I will talk about first the continuous time problem, and then talk about a related discrete time, because indeed in many places, the data is provided in a discrete time setting and influence estimation. So again, some basic information about how do we capture the spatial temporal influence for the discrete events data. So we're going to adopt the famous Hawkes process model, which becomes very popular in statistics and machine learning in the past couple of years. I think many people in the audience might already know this model and become familiar. So it's basically a type of point process model. That's, you can view this as some kind of Poisson, but that's more general. And so you have a sequence of data that happens at random time, T1, T2 over Tn, for example. And so to model this, we can consider the so-called conditional intensity function given the past history, which is a filtration that contains information provided all the past events. The probability of an event at a small interval is captured by this intensity function. This lambda t is a conditional intensity function. So you can see this actually provides a natural framework for prediction, because essentially you say, given the history, given everything I have observed in the past, what is the chance of having an event at one particular time? This is for one-dimensional case, but this can be generalized to multidimensional and also continuous space. And so point process, the most commonly seen one is probably Poisson process. That's like stochastic process number one. You will learn about the point processes where the conditional intensity function, if it's going to be deterministic function. And when this is constant, doesn't depend on time, we have a homogeneous Poisson, but when it varies over time, we have a non-homogeneous Poisson. The Hawkes process assumes this conditional intensity function depend on history. So you have a mu t plus influence from the past. And this is my example of if whenever there's an event, this increases the chance of a future event to happen. So there's a jump. Whenever there's an event, there is a jump. And so this also influence possibly accumulate over time. And so eventually the effect decays, right? So when the crime event happens a year ago, probably don't have any effects, exclude from consideration now. And so the Hawkes process typically assume the influence is positive. There's also the self-correcting process where the influence from the past can be negative. And we can also have different kind of events that have both positive and negative impact. For example, in COVID-19, a hotspot is a positive influence, but a correct intervention scheme is a negative influence. So can we capture this influence from data? Is the purpose here. This is one of the commonly assumed parametric model for Hawkes processes. The conditional intensity function consists of mu t, which is the baseline intensity, and then the influence from the past is captured by this term, which is a summation over the influence over the past events. So this t, apologize for typo, this should be tk. And so this alpha will control the magnitude of the influence over all the past events. And this phi is the influence kernel function that is important, capturing how the past will propagate into the future. And so this influence function in many settings are assumed to be the parametric form, which is exponential decay, but we also, in the next work, want to be able to estimate the phi function itself. In a network setting, we can consider multiple nodes. Each node has one intensity. This lambda IT is the intensity, conditional intensity function for the ith node. And so it consists of this baseline intensity, and also the second part includes the influence from all the past events. In particular, this time this alpha magnitude is going to be a weight that happens on the edges of this network. So alpha ij means how the events happen in j's node influence the events at i's node. So you have this alpha ij. And for example, if in Hawk's process, we want to consider positive influence, we can impose the constraint. This is positive, not negative at least. And so you can see this alpha ij then becomes interesting because then we will understand whether or not this alpha ij is 0 is going to provide information about network topology. That means whether or not there is an influence from one node to another. Second is, you can see this alpha ij can capture direction. So this defines a hidden underlying network that is directional. And this influence function, like I mentioned, most commonly assumed is exponential decay, which is controlled by parameter beta, but we can also generalize this. And we can also learn this influence function from data. And as I mentioned, this is a very hot topic recently. So there has a lot of things being done, starting from work by Alan Hawks in the 70s. There's a good review paper in here by Ringhart in 2018. So both single and multidimensional Hawks processes has been considered. And there is also continuous time spatial temporal modeling. So this is without discrete in space, and it is becoming one of the most important topic in seismology called ETAS model for earthquake catalog study. And also estimating the network interactions. If we know the influence function has been studied in many papers, this is probably a partial list because this list keeps growing. I think one of the organizers, Dr. Yao Xie, has quite a few important contributions to this topic as well, particularly also causal inference. And also recently, there has also been Bayesian models on top of this, imposing prior distributions on the parameters. Okay, so given that, I think what is the missing piece? I should say, okay, probably by now, I shouldn't say very little performance guarantee. There are performance guarantees, but last performance guarantees in terms of uncertainty quantifications of the parameters estimating the model for the model. And so there has been, I think, performance guarantees for the algorithm. For example, the estimation of the network can be formulated as a convex optimization problem if you're focusing on estimating the alphas. And then we can use convex optimization techniques to provide performance guarantees. So lots of new work has been done in this area very quickly. So in the next, I would like to focus on one type of work, one recent work we have on uncertainty quantification for inferring this network. So it's more like a statistical inference task in here, beyond point estimation. And so the motivation is also motivated by answering the question whether or not an edge is going to be 0 in this network. And so because for this particular setting, granular causality can be formulated as inferring whether or not the edge between the two nodes is going to be 0. This is if and only if. So whenever an edge is not 0, that means there is a granular causality between the two nodes. Okay, so people may also question, okay, this is only granular causality. What about actual real causality? So that is a interesting question, and we're also working on that area recently, which is go beyond granular causality, but at least granular causality in this setup is to infer whether or not alpha ij is 0. And so, for example, this is very important for understanding neuronal networks to make scientific inference whether or not the two locations have causal relationship. And so to illustrate why uncertainty quantification is important, I give this example. That's basically what we did the neuronal network simulation. It's a biological simulation. There's a whole simulation package. If we give a true underlying graph, which look like this, and then if we use the existing maximum likelihood estimate, try to estimate the network, this is what the result looks like. So because the data itself is very noisy, it's a stochastic process. And so the estimation result is also noisy. as a result, you can see the true network is much sparser than the estimated, the MLE, maximum likelihood estimate. There are many edges that exist in the estimate, actually are false edges that doesn't exist in the true network at all. And so how to eliminate these undesired edges? One way is to do thresholding. But the thing is, thresholding is artificial. And so I think that the true threshold should come from statistical inference that also depend on the noise level, the number of samples, and somehow intrinsically uncertainty in this model. So that is the purpose here, to be able to provide something like uncertainty quantification or confidence intervals for the maximum likelihood estimate. So whenever that confidence interval includes 0, that means we don't have enough evidence to show that edge is non-zero, then we should exclude that edge. That is purpose here, some kind of confidence interval for our point estimator for these edges. Okay, so the problem is going to be formulated as follows. If you still remember, when we talk about network Hawks processes, we have this alpha ij's, which is critical. That tells us whether or not one node will influence another. And so we can define, for example, for the ith node, a vector. This vector alpha ij contains all the, so maybe let me flip back a few pages here. So this alpha ij's, right? For each node, for example, the first node, alpha 1, we can consider all the possible edges from 1, okay, and form that as a vector. So that tells us how node 1 will influence other part of the network. So define the coefficients for alpha ij's to be alpha I, this is a vector. And then for the point process, we can write down the log likelihood function in closed form, which is this. And one thing I want to say is in this problem, although the data is highly interdependent, because the past will influence the future. So it's not IID, it's not identical, it's not independent across time, it's not independent across coordinates as well. However, we can still, while you write down the log likelihood function, you see this actually can be decoupled as a sum of k terms. K is the number of nodes across the network. So the problem, the optimization problem, objective function in terms of ME actually can be decoupled across nodes. This is used for property, for example, if you want to develop a parallel algorithm that computes this at the same time, each node can compute their own likelihood. So that's, of course, given the parameter. If the parameter is unknown, so some kind of, I think, joint estimation or distributed computation can be developed here, potentially. Probably has been done somewhere in some paper. And so each of the log likelihood function for the node is taking this form that depends only on this alpha parameter at this node itself. And if we know the influence function is given, so for example, exponential decay or some other form, but as long as that influence, how this influence decays over time is provided, then the inference problem, the estimation problem, maximizing over the alpha, so that the A contains all the influence across all the nodes, is going to be a convex function, which is good. And so that means in terms of the estimation problem, this can be solved efficiently and achieve a global optimal solution using many available algorithms such as gradient descent, stochastic gradient descent, Newton's methods, and particularly in our paper using Newton's method, so it converges fast. And so the next question, like I mentioned, is can we provide uncertainty quantification, some kind of uncertainty confidence, confidence interval for this estimate? So we dig into this problem and find, okay, in the past, in classical statistical literature, in the 96, there has been a work done by Ratham, and interesting, that seems to be the only work we find in the statistical literature study this problem, which basically used the asymptotic property of maximum likelihood estimate. And so basically it says the alpha hat solving MLE, this is our estimate of this interaction influence between nodes, converge to the true parameter, and the convergence asymptotically is going to be the difference converge asymptotically to a normal with zero mean, and the convergence matrix is going to the inverse of the Fisher information. So we can write down the Fisher information, no problem, because fundamentally this is a parametric model. And so, and then we tried this and see how good this asymptotic is. And so this is one example where the red indicates, okay, that's our proposed one. The blue one is non-asymptotic confidence interval. provided by this classic result. And so basically, we pull out our example as a simulation, we pull out two edges. And so this edge, the true inference is 0. So that means the edge doesn't exist. And this is another example where the true inference is this place. It's non-zero. And so if you look at what the asymptotic confidence interval, this red one, tells us, so basically it doesn't contain the true parameter all the time when time is not sufficiently large. So this is probably not in the asymptotic regime. That's understandable because it's asymptotic. It needs the t, time horizon, to be large enough. But when the t is not entirely large, and in here you can see this confidence interval doesn't include 0. Okay, so that means if we trust the asymptotic confidence interval, we'll draw a wrong conclusion and believe there is an edge. Okay, and similar here, you can see the confidence interval doesn't include the true parameter at this particular place. So it's pretty, it's understandable because it's asymptotic. It requires the t to be large. And so the challenge is, can we do better than this? Can we develop some kind of non-asymptotic results that can include the true parameter at any given time? So it's called an anytime inference. And so this blue interval is our proposed non-asymptotic confidence generated by our non-asymptotic confidence set. You can see that solves the problem and includes it everywhere. And so, like I mentioned, we want to be able to develop some anytime confidence interval, include the true parameter with high probability. And so can we do that better than asymptotic? What is the challenge? So developing non-asymptotic confidence interval usually is, developed both based on some kind of concentration inequality. And so that's going to be non-asymptotic. It holds any time for any time instance. And however, the challenge here is in this particular Hawkes process setting, we have continuous time that is non-ID. And so standard concentration type results doesn't apply here. And even, and how to construct a martingale, of course. Martingale is the hope, but a lot of the work existing in literature assumes discrete time setting. And so we need a stronger result, which is some kind of continuous time martingale construction, hopefully can give us a desired result. And in particular, we also face a network setting. So we have alpha ij that we want to infer for each edge. So we have a multidimensional problem. Can we perform a simultaneous confidence interval, or maybe beyond confidence interval, which should be a confidence set fundamentally captures where these true parameters should lie in the space. So we want to be able to go beyond confidence interval, but consider general confidence sets as well. So that is going to be the goal here. We're going to leverage a recent development in non-negative super martingales and use it here to find our martingale that can provide this kind of confidence set that is not an interval, because if you consider interval for each of the coordinate, in the end you have a box in high dimensional space. The box is very crude approximations. We want to be able to hopefully come up with a general confidence set that contains the true parameter with high probability. All right, and so that's the main question here. And the main idea in developing the result is the following. So we revisit what has been done in statistics for this type of results. Is the so-called delta method. It's based on the mean value theorem. Basically, if you look at the so-called score function, which is the derivative of the log likelihood function. And this score function is going to be 0 at MLE. That's a property of the maximum likelihood estimate, because you want to solve the maximum likelihood estimator to maximizing likelihood function. So the derivative at that particular point is 0. Okay, and then you consider any other alpha, the difference between the two. For example, when this is close to the MLE, then we can write it as the second order derivative, which is related to the Hessian of the likelihood function, which is related to the Fisher information, times the difference of the parameter. Okay, so this is a useful connection, because then we can invert the Hessian, and then this can tell us the difference between the true and the MLE in terms of the this function. So this is going to be the inverse of the Hessian, asymptotically converged to the Fisher information. And then the second term is going to be this side. This is going to be the score function at another alpha, and then this is 0, so it doesn't exist here. So we want to use similar kind of idea here and be able to quantify this quantity here, which is the inverse of the Fisher times the score function. And this is a k-dimensional vector, consistent, because this is our parameter for each of the nodes. This is optimization problem decomposed over nodes. And so if we can somehow be able to provide a anytime concentration bound for each of the entries in here, then we'll be able to construct our desired confidence set. All right, so this is the main result. And so bottom line is we can construct a another thing I want to mention before we move on there is, so basically there are two things going to be happen. One is that this score function is a continuous time martingale, which we can show and relate it to that general framework. And the second one is we can also perform an adaptive estimate of this Fisher information from sequential data. So combine the two results, combine the two, we can construct these confidence intervals, confidence sets. And so the confidence sets are in this expression for each node. Remember, for each node, we're interested in inferring all the associated inference parameter. And so these alphas are going to be contained in the set with confidence level 1 minus epsilon. So for example, in statistics, you'd say, can you tell me a 95% confidence interval? So that's going to be 1 minus epsilon is equal to 0.95. So epsilon is 0.05, significance level is 0.05. And so this set is described by these by 2K inequalities. And what are these G's? These G's are basically coming from the characterization of the continuous time martingale. And so the V here is a so-called intrinsic variance. And what is a Z? Z is going to be basically, remember we have to invert the Hessian. And so the Z is basically resulted from the inverse of the Hessian. And the inverse of the Hessian is going to be estimated from the past data. And then this DSI is basically, this is going to be the score function, right? So basically, this G is a result from the continuous time martingale analysis. And so you can see this upper bound, of course, is controlled by our confidence level and also the number of nodes in the problem. And so this is the main result, but it's not entirely transparent. So we want to have some practical algorithms to be able to use this as well. And so first of all, we characterize the base of the confidence. This is a confidence set because this describes the set where this vector lies in. It doesn't just say the interval for each of the entries. So this can be a set. But if you want to understand what is the width of the set in each of the coordinates, it is consistent with what we know for asymptotic results. And we can actually show that the width of this confidence set, if you see for this particular coordinate, and that's going to be in this level. And in terms of the scale, this is matching the scale of the confidence interval for the asymptotic results. So we know that it is reasonable. And based on this result, we also can come up with an like I said, this is not transparent. How do I even come up with this confidence set? Given these complicated expression, can I actually use my data to come up with this set? And so we come up with this polyhedron confidence set approximation to this general set. You can imagine if the original set is like a cloud, now I impose 2K edges, 2K faces, each one of them is linear. It's a hyperplane to carve out this confidence set, okay? And so basically in a high level, this is going to be solving a linear program, feasibility problem for a linear program to cover out 2K faces for this confidence set. All right, to just to give a very, very simple example to see what this confidence set looks like and how is it different from asymptotic results, we consider very simple network with only 2 nodes, 4 edges like this, and alpha ij's is 0.2 for the ice node. And so T time horizon is this, and then the baseline intensity is this, D, the number of nodes is 2. And so this is what it looks like here. And so here the red shaded region, which is in this, this box, is the asymptotic confidence interval. And because it's a confidence interval for each of the parameters, so it's going to be a box. And this blue shaded region is the polyhedron confidence set. solved from our problem using that algorithm, you can see it's not a box, right? It's actually some kind of parallel shaped. And so this, these edges are tilted. And so the true parameter is this, this yellow dot. You can see indeed somehow it's excluded from the red shaded region in this example, but it's included in our blue confidence sets in here. All right, so how does it work in practice? So we also tested on the neuronal network. Like I said, this is one of the motivations here. And so the data is generated by Alex Kuzo, and this is in collaboration with Simon Mack, one of our Georgia Tech alumni, currently assistant professor at the Duke Statistics. So we collect these data, and this example was explained earlier. If this is the true network, and this is MLE, and then using confidence interval, then besides these point estimators, we can also have a confidence uncertainty for each of the estimate. And when that particular estimate doesn't include 0, that means that particular edge should be included. But when that confidence interval includes 0, like I said, that means we don't have enough evidence that should be eliminated. So based on this, we compare if we use that scheme, we can eliminate many of the noisy edges that shouldn't be in the true graph. And we also compare the 95%, if we wanted the coverage to be 95%, then our proposed method, the coverage ratio is 96.8, so achieve the target pretty precisely, versus asymptotic coverage ratio in this here rate is 100%, means that it's over covering, so it includes many unnecessary edges. And also we can have an overall narrower confidence width in this example. So the answer quantification is also more precise in this example than the asymptotic example. All right, so with that, I think that finishes my first part. So I want to briefly talk about the second part and then some extensions. Okay, the second point is about influence estimation. Like I said, in the previous one that I talked about, we focus on estimating this alpha edges that provides information about the network, underlying network. And we provide ancillary quantification for this alpha, so we can know whether or not the alpha is, exists, but also, besides just a point estimate, we can also have a confidence set. And now the natural question is, what does phi should be? Is it just a exponential function or something else? In particular, even in this neural network problem, there can be a delay of the influence, right? Exponential decay means that whenever there's an event, then the influence happens immediately. The trigger effects also decays over time. But in practice, in the theory, in neural network activities, it should be like this. There should be a delay. And so you can think about this in for example, COVID, right? Whenever there's a hotspot, it doesn't, the hotspot nearby doesn't happen overnight. There's going to be a delay. So the influence itself will have a delayed effect. So if there's a delay, that means this particular phi function is probably not exponential, but maybe some other shapes, for example, like this. So can we estimate this, go beyond this and estimate this, function as well, for example. And so, and then what's the difficulty? If we imposing a parametric form on this phi, for example, if it's exponential decaying with decay parameter beta, then we come back to the maximum likelihood problem. And before, when the phi is fixed, the problem is convex. But when the phi has a known parameter beta as well, then the problem is non-convex. So estimation that way is going to be difficult. It's non-convex optimization problem. And the second is, if phi is unknown, the likelihood function will involve some integral. That integral is over a high dimensional space. So that's going to be difficult as well. And one of the most well-known challenge in MLE, when we don't have integrable phi, some exponential decays is one of the cases where the integral can be solved in closed form. But if you go beyond that, the numerical integration is going to be prohibitive for many problems using MLE in this setting. So because of that, we consider the following reformulation, which basically consider how do we capture the influence between events at different times and location in the general terms without having that parametric assumption. And so I'm going to talk about this very briefly, maybe the high-level idea, and the paper has been published in this paper. If you're interested in checking out, you can find this on my website. And so consider this. For example, we have a discrete. This time we discretize the time into very small intervals, and there's observations at different nodes. And the memory depth is some d. So this, for example, in exponential decay, the beta roughly controls how quickly or how fast the influence decays over time. And then to simplify, we can assume the observation is binary. And so there are some events here, and then how those events will influence another events in the future. And so if you assume the space and time grid is sufficiently fine, and then there could be one event happens or no event happens. That's why we consider this Bernoulli process as an example to start with. And so we can assume that the probability of having events given the past is specified by this model. And so it's like a generalized linear model, actually. So this mimic the baseline intensity function we had before. And now this time, we're going to have this beta KLS, which is the influence from node L to node K as period ago. You can see this time, this beta is like a tensor, right? Some kind of tensor parameter that contains the influence between location at different times at the same time without decomposing them. Okay, so now, and we can also, in order to make sure this is a valid probability between 0 and 1, having some link function outside. This can be sigmoid function or something. Okay, and so the sigma function is going to make it interesting, that I'll mention. So the problem now is to given all these observations, omega, to estimate these parameters. Okay, and so also would like to mention that this model is related to the so-called feed-forward RNN or autoregressive model in deep learning. So just pointed here, we find interesting this interesting connection that has been similar kind of model has been studied in this setting. All right, so coming back to here, how do we estimate this beta parameter? And so, like I mentioned in this model, we possibly will need to include some link function here. This link function could be sigmoid if you want it to be between 0 and 1, or if this if you want this to be something else, this can be ReLU or tangent H or something. Like in here, of course, you're going to consider some other link function. And so that link function, if we write down the log likelihood function with that sigma or least square estimate, it's going to result in a non-convex problem. And so we want to be able to solve this and with some performance guarantee. And so there is, I think this is probably one of the main message here is we can solve this problem, convert the non-convex problem into convex problem using its variational inequality trick that has been studied and presented in this paper by Juditsky and Nemrovsky, 2019. And so basically there they studied the estimation problem for GLM. So we saw this paper and thought, oh, okay, we can actually use a similar approach here because this is the GLM, generalized linear model in spatial temporal setting. And so basically the idea is instead of solving optimization problem by minimizing some objective function, and then if you plug in MLE or least square, it's going to be non-convex. But then I'm going to solve the so-called variational inequality by constructing this monotone, this F, which is induced by the monotone operator. And so finding a beta such that this holds everywhere. So what is this F? This F is almost like a gradient, but it's not quite. Okay, it can play a role of a gradient, but why we constructed this way is because then this problem is going to be convex. Okay, so I guess don't have the complete time, but just want to highlight the main idea. So essentially this F can be interpreted as a gradient, but it's not the gradient of, not necessarily a gradient of a function. So for example, when the function, when we can consider the least square problem, when this link function is linear, then the gradient of this objective function is going to give that particular form. All right, so because solving VI is convex, so we can have these performance guarantees in terms of recovery of the true parameter betas, captures the baseline intensity, the influence between nodes and over time, everything together. And we also have some simulation, shows this works in practice pretty nicely. For example, in this simulation example, the influence between nodes are not going to be exponential decay. They're general shape, and it can have a delay. It can also become small and large and become larger. So it's not going to be a stationary process for sure as well. So not a traditional setting. And so you can see the estimation can match with the ground truth pretty nicely. And we can also, because this is a pretty general setup, and we estimated these betas, this is going to be a lot of parameters. We can also introduce any desired structure. For example, we can assume this beta is a low rank tensor, and that captures the unimodal structure of the inference, right? So for example, the Gaussian diffusion kernel is unimodal over space and time. When I discretize it, the resulted beta is going to be a low rank tensor. And so we also studied this regularized beta estimation in this draft. And so this can be extended to categorical observations beyond just Bernoulli, but you can talk about these for each location, the AMS type of data or no events. And so this can be used for marked point processes modeling. I guess I can then example, we use this to study crime data, Atlanta crime. So consider burglary, robberies, the two categories, and discretize the location and the time. And so this is the estimation results. You can see these black edges indicating the potential influence between these different locations. This also varies over time, which is quite interesting. For example, this particular subplot here shows the influence of if a robbery happens at one location, how this will trigger future burglary. And there seems to be some connection. And this influence happens, changes over time. It doesn't, it actually grows over time in this particular case. So there seems to be some delayed effects. And so whether or not this is a reasonable model, we also have a check, for example. Like I mentioned, this is a natural framework for prediction. And so we basically use this to predict the chance of having a burglary robbery in that region of Atlanta and match this with empirical frequency. And so this is the true frequency, you can see. And this is the estimation, the prediction. You can see the numbers. Of course, it's a small probability. The good news, it doesn't happen very often, so it's a small probability. And so the probability seems to be matching. For example, here, the truth is 0.14, and the constraints, we consider two estimations, one with constraints and the other without constraint. With constraint means we impose some regularization terms, seems to be matching, which is kind of surprising to us, I think, because it's such a simple model, but seems to be capturing some ground truth. And also want to mention that we are also applying this to model solar power ramping events. This is a type of anomaly events of happens over space and time. For example, you have a solar panel, and then the solar panel, if influenced by the weather, when the weather is bad, then you have a dip. So we want to be able to make a prediction about that. So we use the spatial temporal point process I mentioned there. And we also generalize that approach to model Hawkes processes. This is useful for studying COVID-19 data. All right, so this can be extended to, like I said, including contextual information combined with machine learning models, such as neural networks. And so also detecting changes, just want to mention very quickly, getting back to here. So in the past, we basically assumed this influence kernel, for example, is alpha ij times exponential decay, or this influence kernel is going to this beta. So beta with, this beta ijk's captures the most general influence, but we can also represent this influence kernel using something. And for example, I have some recent work if you're interested, checking out, representing this as a mixture of Gaussian diffusion kernels where the underlying parameters are controlled by neural networks. And we also have a work that we can consider a spectral decomposition of this kernel function, where the kernel maps themselves are represented using neural networks, which is in this recent paper here. And so this can be useful because then we don't have to discretize space. So this is going to be continuous time, continuous space, and the inference functions themselves are going to be learned from data as well. And this can be interesting. One last story for the talk is, for example, look at the seismic activity in North California. And this is the so-called ETAS model. ETAS model is the status quo that being used by the seismologist. And so this is what the ETAS model tells them, how the influence of earthquake propagate. And so it's not very specific, it's blurred because the underlying kernel is a Gaussian diffusion. And so this is basically captured by our model. The flexibility and expressiveness is enabled by underlying neural networks. You can see this captures, there are, once the seismic activity happens here, earthquake happens here, the influence propagated along these two directions. And so we show this to our collaborator in seismologists, and they're pretty excited about it. And they can tell stories saying, oh, this is because this is the St. Andreas Fault in California, and this is another fault, and there's something happens in the Pacific Ocean. So that's why it propagated in this direction. So that's something I think enabled by expressive power of the kernel here. And we also use this for crime data and some fancy stuff. Our collaborators in Atlanta Police. And so thank a lot for all the collaborators contributing to this and the general support by National Science Foundation. All right, that's it for the talk today. And sorry for using up all the time. And thanks a lot for your attention.
Thank you so much, Professor Xie. It's a very nice talk. And as for the questions, also there are a few questions in the chat box. So the first question is how to define a space-time kernel function.
Okay, sure. Let's go back. Let's see. Yeah, so this is one example of the space-time and mark. So basically, so we expanded, but basically you have a time. So it's a kernel basically means that it should have two interactions between two entries. And so this basically captures how event happen at time tk, location xk and yk. In this case, it's for example, xk represent location and yk represent additional information like marks. Right? So it can be high dimensional. And then the t, x, and y are the candidate time, location, and the marks in the mark space. And so this is going to be the kernel function. The most general kernel function captures inference between any location time and this particular mark in terms of similarity. And this doesn't need to be, oh, sorry. This doesn't need to be positive. It doesn't need to be PSD. So it's more like if you are familiar with the system models in control theory in electrical engineering, this is like the so-called impulse function or transfer function. If you give an impulse, then how this will, how the system will react to it. So that's an analogy here. All right, thanks for the question.
Oh, thank you. And a following up question is, how would different kernel functions other than Gaussian affect the result?
Yes, okay, that's a great question. So I think this is an example. So this basically is this third panel is fitted using Gaussian diffusion kernel. When this V is a Gaussian diffusion. So Gaussian diffusion means that in a space for any given time, it's a Gaussian. And over time, it diffuses over, there's a T parameter as well. So using Gaussian diffusion kernel, this is the, this is the result, what it looks like. So you can see the Gaussian, the problem is that Gaussian diffusion is, first of all, usually when we consider the kernel function that doesn't change over location. And so it's pretty uniform. You can see it doesn't quite tell the information how the influence propagates. And this is changing the Gaussian, like vanilla Gaussian diffusion to Gaussian diffusion where the underlying parameter is controlled by the neural networks. And then you can see the information is pulled out from data much better. You can see this actually, for each location, the influence can be different. So that's basically the idea here. And more generally, what about other type of influence function, even beyond Gaussian diffusion? For example, this recent work, neurospectral mark point processes, where basically the idea is to decompose this V using representative theorem. So this can be represented using a combination of feature or basis functions, but actually this basis function doesn't need to be orthonormal, they can be feature maps. And then it basically represents all the interactions between them. So why we consider that is because when you have more complex data that, for example, the police reports where you have a very high dimensional mark, which is the entire police report. Like, for example, you can use embedding to map that, natural language processing part into some embedding space, but still it's high dimensional. And so how to handle the high dimensional marks together with time and location, we need those more powerful kernel function beyond just Gaussian, or Gaussian diffusion, or a mixture of Gaussian. So represent this kernel using spectral decomposition and learn the kernel from data will enable us to achieve that goal. Does this answer the question, sort of?
Thank you. And another question is, when it comes to the to neural networks or kernel version of neural network, do you have some theory for the approach you proposed?
Yeah, yeah, that's a great question. So this is very recent work. So basically, this paper, I guess you guys probably guessed this is submitted to NeurIPS. Fingers crossed. So basically, if you're interested, you can take a look at this archive paper here. Basically, there's something theoretical can be said in terms of that. So the theory is basically, we know that neural networks is a universal approximator. So there's an approximation theory part of saying if the neural network is, wide enough, for example, or the number of layers is large enough, then it can approximate the arbitrary function universally with small epsilon. And so basically, we can say, based on that, there's some functional optimization guarantee. Means that if we solve a functional variation problem, if we solve maximum likelihood, where the argument is going to be the kernel function. Of course, it's a function, so we want to find the best kernel function in the function space. Then solving maximum likelihood is actually going to be asymptotically convex, or if it's high probability is convex in the function space. And so that means if you have a good function that can represent a kernel function, so that good function can be neural networks, and then it can, with high probability, converge to the true kernel function. So that's the type of guarantee we have here. But of course, the exact guarantee is going to be difficult because neural networks, anything involving neural networks is non-convex. There has been a lot of theories said about the algorithm property, but it's going to be more challenging. So to simplify the theory there in this paper, we basically can establish in terms of the functional optimization variation problem, using MLE can lead to a convex problem with high probability. And then that means if you use neural network to parameterize the true parameter, true kernel function, actually not directly parameterize, there's another step going on, which is to parameterize the feature maps. The product of the feature maps gives the new function, and the spectrum of the kernel is also represented by neural networks. But hopefully that gives a rich enough representation, then it's likely to converge to the true kernel. So that's the kind of guarantee. Yeah.
Thank you. And another question is, are there some standard forms of space-time kernel functions?
Oh, yes. Okay, standard form of space-time kernel function is a Gaussian diffusion kernel. Basically this, right? The result obtained here is by Gaussian diffusion kernel. But one thing I want to say is Gaussian diffusion kernel is continuous over space and time. And so a lot of the work I presented here, for example, the network setting, essentially it's discrete over space, right? So we consider network. There is pros and cons considering that. Because Gaussian diffusion kernel essentially assumes the influence between two locations decays over their distance, which may not be true. In COVID-19, right, you consider New York City, Atlanta are not very close. New York City and San Francisco are not very close. However, there's direct flight between them. And so the influx of these people is going to make a strong correlation or influence between them. And this can be captured using network set because you can place an edge between New York City and San Francisco. But using Gaussian diffusion kernel, that's not going to be achieved unless you make the kernel bandwidth to be infinite, very, very large. That's not useful. So, some, combination maybe of, Gaussian, there's pros and cons basically I'm saying, but the cons is that if you use network discretization of the space, you may not be able to see this kind of continuous pattern over space that have this interpretation. So yeah, so that's the two approaches.
Thank you. And also another question is it possible to incorporate, say, node contexts? What if there are contexts associated with nodes? It seems from this kernel representation, it can be naturally incorporated into the kernel function.
Yes, that's right. That's a great question. So there are many potential extensions to this. I think I may have a backup slide here I can show to you. Yeah, this is one example. For example, the events data essentially has the information on the edges, right? On the events, right? But there can also be information on the nodes. So what does it mean? That means, to give an example, so kernel function is one approach, like Dr. Yao suggested. I think that's possible. But also, for example, for each location, you have some additional information. In this power outage study, the baseline can be, for example, different locations. And some place you have more outage because of storm. In some other location, you have more outages in Boston area because of snow, right? So these additional information we call the endogenous factors can be incorporated into this mu part, for example. So this has been studied. Also in for COVID-19, for example, the population density for each location and socioeconomic status, these are associated with each of the node, each location that can be incorporated into the model as well.
Thank you. And maybe it's our last question. So it's raised by Chuck Coleman. The question is, how do the solution change in the presence of measurement error and missing data? And have you ever have you considered imputing the missing data in the algorithm? Okay, that's an excellent question. Glad this is being asked. So I haven't studied missing data ourselves, but there has been some work I know in the literature studying missing events in Hawk's processes. For example, you can have a sequence of events, right? So somehow one event is not observed. That's being excluded from the history, right? So that's going to cost the information. And so I think that's a very interesting problem, and that potentially can be addressed using the likelihood-based approach, right? So you can, for example, there's something happens with great magnitude, and then you try to fit using past observation, and then you find out you couldn't explain that particular magnitude event at that location. So that indicates there's possibly something missing in the history that hasn't been recorded. And so I think approach has been tried, including expectation maximization and these kind of approaches. So I personally hasn't studied the missing data problem, but I think it's a good question. And then there has been some work done for missing events. And some people I know, for example, 2018, there's a nearest paper, they called it the time back propagation. So basically they say, what if I can, given the current events, infer what has happened in the past, right? Tracing back in time. And it's possible, possible to build on top of this point process model as well. So there's another question regarding the measurement error. I think depend on how we define the measurement errors. So basically, there's randomness. First of all, there is randomness in our data. The randomness is because there are realization of the point processes. So I guess the question is about what if there's an additional source of error other than intrinsic randomness, like Poisson, for example, additive Gaussian. I don't know, depending on the setup, engineering problems, it could be in Poisson problem, there could be some additional error on the intensity function, I assume. For example, somehow the number of cases being recorded is too low, and there actually are more cases. And so that's additional resource here. I think those can be studied as well. I personally haven't studied them yet, but I think possibility includes, having the model including in error. And I know there has been study using Bayesian approaches where you have more complex point process model where the noise part can be controlled by another random variable together with this. And you can also even impose prior distributions on the beta. So for example, one of the colleagues in the field, Dr. Abel at the University of Washington, and he has some work done in Bayesian Hawk's processes. I think that potentially can be used here. Yep. I hope this helps with the question. Yeah, thank you. So due to the time limit, I think that's all the questions. And thank you again for your time. It's our great pleasure. Great, yeah. Thank you so much, Dr. Yang, for hosting, and thank you all for attending the seminar and great questions. I really enjoyed all the interactions. Thank you all. Yes, thank you. Okay, we'll be in touch. And let me know if there's more questions, just send me an email. Thanks. Thank you. Bye, everyone. Bye. Bye.